Measuring angles and positions on the sky is one part of doing astronomy and improving the field. But another important part involves timekeeping, and we'll see why. Timekeeping is central to astronomy. It was central to progress in astronomy and also in navigation. Why is timekeeping important? Well, the quest for the size of the solar system and the distance to the stars, two major innovations that happened in the 18th century, relied on parallax. You can measure angles, but as we've seen in these small, skinny triangles, you need one side of the triangle to set the scale. That means you need to know longitudes. You need to know local time accurately. We'll get into this in detail. You can get an astronomical measurement of local time, i.e. from meridian transits, of how a star or the sun passes through its highest point in the sky. But you also need a way to get local time for any time of day or night, and you need to be able to measure intervals of time to time transits and occultations and eclipses. But more fundamentally, and actually more importantly, since commerce depended on these innovations, timekeeping is crucial for navigation at sea. It's very straightforward to measure latitude with the elevation of stars using a sextant, but to measure longitude on a planet that's spinning in space, you have to know the local time. Errors in navigation through the 15th, 16th, and 17th century led to the loss of hundreds of ships and thousands of lives every year worldwide. It was a huge problem. And as nations became global powers and seek to extend their reach beyond their shores, they needed ships that could navigate. Trade, commerce depended on it. Military conquest depended on it too. So navigation, to recall, depends on measuring two angles, as does astronomy. The latitude, which is the angle relative to the Earth's equator. Because the Earth is spinning, the equator projects out into the sky in a routine way, and you can measure the elevation of a star to get your latitude, with the pole star perhaps as a reference for 90 degrees. But longitude is trickier, because the Earth is spinning, and so the stars pivot overhead at a rate that depends on the spin rate of the Earth and can only be calibrated by measuring local time. Here we see a montage of the various instruments of navigation from this period of time, and here we'll see them animated.
I took a trip on a great big ship to a land across the sea, to a land across the sea, the sea, the sea, the sea, the sea. When far from shore the sea I saw, and the saucy sea saw me, and the saucy sea saw me, saw me, saw me, saw me, saw me.
So let's connect with what the real issue was here with navigation, with doing astronomy and also navigating at sea. We have a situation where the sky rotates through 360 degrees in 24 hours. That works out to 15 degrees per hour, 15 arc minutes per minute, and 15 arc seconds per second. So an error of 5 minutes in time for the sky that pivots overhead is a 1 degree angle. And so being uncertain by 5 minutes means you can't locate an object within 1 degree. And remember, this is not for stars you can see with your eye. Astronomers are now working with faint stars, too faint to see except with a telescope. So you need to be able to point your telescope accurately to even find a faint star. And if your clock is uncertain, there's no way you could possibly find it. The fundamental issue that people are wrestling with at the time is seen on the right. It's the solar parallax. Astronomers are trying to measure the small angle subtended by the sun from two different places on the Earth's surface. Because if they can determine this angle, the solar parallax angle, then in that equation, knowing the diameter or radius of the Earth, you can get the distance to the sun. And this will set all the scales of the solar system. So the quest for the solar parallax was a very foundational element of astronomy of this time. Its value has now been computed to be about 8.8 arc seconds, under 10 arc seconds. So you can see that it's one of these very small angles that would be very difficult to measure. From the navigation standpoint, the Earth spins at 1,200 kilometers per hour at a mid-latitude like 45 degrees. This corresponds to 20 kilometers per minute. So a clock, a ship's clock, that was 5 minutes off after a 3-month sea voyage would leave the ship uncertain in its position in longitude by 100 kilometers. That's easily enough to miss a small island, to stray onto a reef, and of course, many of the shipwrecks of the time were caused by this. So we can see how critical it is to have accurate clocks for navigation. The best clocks of the time were called verge and folio clocks, and they had an accuracy of only 1 minute per day in the 17th century. And remember, that number would get a ship off target by 100 kilometers in just 1 week. So the clocks were wholly inadequate to the job of navigation on the seas. So what did people do? Well, they did estimation, they did rate of motion of their ships, and they did dead reckoning. And of course, they depended on features. They often followed the shorelines, but for the large ocean voyages, they were stuck with using the stars and the sun. Building on Galileo's pendulum investigations, Christian Huygens adapts the pendulum to an existing clock design. A pendulum is a universal timekeeper. The period of a pendulum depends only on its length, and it's independent of the amplitude of oscillation. This was the realization of Galileo as a young man bored in church. And this means it's a very good basis for timekeeping. So you just needed a pendulum, a device to protect its motion, so it's not subject to winds or buffeting or vibration. You need a device for counting the swings of the pendulum, and you need some way to make up for friction in the air and the mechanism itself. And these last two needs for a clock are combined in the escapement mechanism that we see to the lower right. A falling weight wants to fall quickly, but the escapement allows it to fall 1 tooth per swing. And so the escapement is a way of taking a pendulum clock or a clock that's driven by a falling weight and slowing the falling weight down so the clock can last for a while. The force on the pallet gives the folio or pendulum a slight push. Huygens rotates the verge to horizontal, and the pallet shaft becomes the pendulum pivot. With these innovations, the accuracy jumps from about 1 minute per day to 15 seconds per day. That's an improvement by a factor of 4, but it's just still not nearly good enough for the long ocean voyages. About 1670, clockmakers and Robert Hooke, working in England, invent the anchor escapement. This allows amplitudes of only 5 degrees, but it also allows pendulums to be in a convenient clock case. A pendulum of a length 39.1 inches, just under a meter, by the laws of physics, beats once per second. Less power is required to run it, so the falling weight lasts longer. A pendulum clock, once wound and the weights raised, could last perhaps for a week. It also reduced the wear on the mechanism, giving better long-term accuracy. So this innovation leads to grandfather clocks, or regulator clocks as they're called. What's called a deadbeat escapement, developed around 1675, reduced even further the friction and recoil. So by this time, the end of the 17th century, we had very good clocks for keeping time on land in daily life. But these clocks are still too large and cumbersome to use at sea. Further innovation is needed. And this is spurred by something called the Longitude Prize in 1714. Here we see a picture of John Harrison, famous clockmaker and builder of the world's first compact marine chronometer. He's holding it in his hand proudly. There's a marvelous book written by Davis Sobel called Longitude about this story of how longitude was solved as a problem and how John Harrison did this as a lone genius, essentially. The story of Davis' book is also interesting. She went to a conference, or sent by her magazine or newspaper to a conference on longitude, thinking it would be the most boring conference she could possibly attend, so she took plenty of reading. Instead, she found this historical conference about longitude was incredible because it told pieces of this amazing story of John Harrison, and so she knew she had to tell this story. Longitude, the book she wrote, I think it took 20 publishers before she found a home for it. It became a bestseller, and it's a beautifully written and compelling story that I highly recommend. Here's Harrison's first clock and his best and last clock. Notice how he's improved the mechanism and made it compact enough to hold in your hand. And yet this is a chronometer that's good enough for a sea voyage to rescue millions or even billions of dollars of commerce from shipwrecks and the problems of navigation for the previous centuries. The marine chronometer and the prize that Harrison competed for was spurred by a very particular naval disaster in 1707 in the Scilly Islands, where there was the loss of 4 ships and 2,000 lives. It was a huge embarrassment to the British Navy because it was caused purely by poor navigation and poor judgment. So the British Admiralty offered a prize of £20,000. That's worth several million pounds or dollars, present-day prices, for a new and accurate chronometer. It was called the Longitude Prize, and Davis Sobel tells its story. After many years of work, John Harrison's best prize far exceeded the spec for the prize, and in the final test lost just 3 minutes after an 80-day, almost 3-month sea voyage. We can see the features of his chronometer, incredible details that he worked, countermanding mechanisms to reduce systematic error and friction, amazing innovations he developed in sequence, along with making it so compact it could fit in your hand. The story almost and really did have a bad end because he never got all the money he was due, and he had to fight for even a part of it. The problem was Harrison was outside the academic or professional community. He was self-taught. He had nothing more than a middle school education, and he essentially was resented by astronomers who had made major errors in the past. They were to blame for a lot of this because they hadn't solved the problem. And there were other inventors, more famous than he and richer than he, who didn't come close to matching his craftsmanship. But he persisted. His chronometer was the one that solved the longitude problem and made world navigation a whole different thing. That's the end of this topic.